Okay, so here's the situation down in the lower right-hand corner. And so what we want to do is pick up where we left last time. So it's a new example with rate function r. And what is our goal? Our whole goal here is what? You know what the rate is at every moment? Or you know how fast a quantity is changing at every moment? And you want to know how much you have at every moment. So this is the idea of function, right? The idea of function that we want to be able to pick any x value here and know what the current accumulated amount is, given that we have the rate function. Okay, so we did this on Friday. Let's see how it goes. So I've set up the first 4 moments here, from 0.5 to 2, 2 to 3.5, 3.5 to 5, 5 to 6.5. Within each of those moments, dx will vary from 0 to 1.5. And so can you write how many? So can you write these lines of this function that if you input a given x, it will tell you the total amount accumulated up to that value of x. Okay? So why don't you try for a couple minutes? Get help if you need help. But we got to make sense of where this accumulation function comes from if we have the rate function. So take a couple minutes. See how you do constructing this. Don't try to look at Friday's notes and just copy Friday's notes, right? See if you can do it by reasoning it out like you're doing it for the first time, okay? And we'll walk around and help you, okay? I'll just write it. No roughing. Use XS. That better? Yeah. Okay, so in this first interval, if for any dx, how much accumulation do you get for any dx starting from 0 here at x equals 0.5? Dx starts at 0. For any dx from 0 to 0.5, how much accumulation do you get? Who thinks they can write the equation or the expression that will give the total amount of accumulation in the first interval due to a change of x of dx? Should be able to do this. Given a change of x of dx, how much accumulation do you get? Please, maybe one person? Go for it.
0.6 dx?
0.6 dx. Where's the 0.6 coming from?
Is that what? I can't really see the numbers. I'm assuming that's 0.5.
We're not estimating. We're using exact values for the rate. We want exact expressions for the rate. Yeah. No. With the long, pretty red hair. Thank you. So, dx, what's the amount, the change then in y, the change in the dependent quantity will be the rate times dx. The rate times dx. Did we have any accumulation from before? No. So the only accumulation we have in this first interval is the current rate of change times whatever change in x we have. dy equals mdx. Right? The change in our dependent quantity is the rate, which is r of 0.5, the rate taken at the left side, dx. Okay, so now we get to the second interval, and we start with some amount of accumulation. How much accumulation do we have at the start of the second interval? How much? So dx is 0. How much accumulation do we have when dx is 0 in the second moment? Anybody? We've gotten to x equals 2. dx is 0 in the second interval. How much total accumulation do we have? Yes, sir?
R2 dx plus R of 0.5.
Nope. We're at x equals 2. Total accumulation up to this point. Joseph.
R.5 dx
And dx, but
is 1.5.
right. So at 2, now it's going to be r of 2 times 1.5. What? Plus the additional accumulation in this interval for the new dx. And how much will that be? No. dx. It's a changing quantity. Again. R of 2 dx. Oh, I didn't hear you. I'm sorry. I'm very sorry. I'm very sorry. Okay, I'm not ignoring anybody. Okay, so we have the total accumulated from the first interval, which is going to be that rate for the whole width of the interval, 1.5. Plus now, whatever dx we have in that second interval, times its rate. Okay, try the next two lines, see if you can do it. Don't just follow the pattern. Think about the meaning. What's going on? Don't just follow the pattern. Okay, so when we get into the third interval, we have the accumulation of the first two intervals. And we know exactly what that value, we know exactly how much accumulation we have. We have the accumulation from the first interval, plus the accumulation from the whole second interval, which is what? Or the whole second moment. What's the accumulation from the whole second moment? R of 2 times 1.5. That total change in independent was 1.5 times the rate, which is R of 2, gives us the change in the dependent. All right, and then we're in the third interval. How much change do we have if dx varies through the third interval? R of 3.5 dx. So every time we move into a new interval, we're keeping, now we have another completed interval, right? Every time we move into the next moment, and dx varies to the new moment, we knew exactly how much change or how much accumulation we had in another full interval, completed interval. So then it'll be this for the last one. And we'll just keep going like that. What's that? Okay. Okay, so questions before we move on. Questions? Yes, please. No, we don't. In the current interval, it varies. That's the whole point. It varies in the current interval. That's why this is a function, because we can get the total accumulation at any x value here. And so if the x value is 4, now we're in the third interval, and dx is taking on a value of 0.5. And so we add on half, or 0.5, times that rate will be then the additional accumulation to get the accumulation total at 4. dx is varying in every interval. So you saw those animations in the book, right? dx varies. Interval complete. Now dx starts over. New interval complete. dx starts over. Other question? Yes, please. It could. So I could have put less. I'm just doing the exact same thing he did to be consistent with the book. If you put less than or equal to, then you would put in 0.5 and you'd get 0 accumulation. So it'd be okay. It'd be okay. Other questions? Okay, so what we want to do is we don't want to write this in a. So what's going to happen? We're going to make the moment smaller, because that's what's going to be realistic. And what's going to happen to this function when we make the moment smaller? We're going to have hundreds, maybe thousands of separate lines. We don't want that, right? That's too cumbersome. So what we want to do is we want to write this function in one rule. We want to write this function in one rule, and that's what you should have read about. So we want to summarize what's going on here. What does this represent? So there's really two parts to this. There's this, and then there's this. What does the first group represent in that line? Function. Yeah. Okay. It's the total accumulation from the completed intervals. The completed intervals. That's the total accumulation from the completed intervals. And then what's this? How much accumulation you have in the current interval, right? Which varies. That's varying. Okay, that's varying, but this is fixed. As soon as that one gets done, then we add another completed interval into this, and we start varying in the next one. So what we want to, in order to write this in one line, we're going to use our summation notation. Summation notation, which we learned about. So this is going to be a sum for completed intervals. And then this is going to be the additional accumulation for the partial interval. Is it important? Do we need it? Yeah, last time in class we did the example for the racket basketball at 5 seconds. And before we added the additional amount on, it was something like 10.75. And when we added on the partial interval, it jumped up to like 14 point something. Very important. It's a huge difference. Okay? So this is crucial. You can't just do completed intervals. You have to have whatever that accumulation from that last partial interval. Okay? So here's going to be the general structure of this function. We're going to sum up completed intervals. Every completed interval is going to be our delta x, the width of a moment. We always multiply by 1.5 over there. Okay? So this will be r delta x, and we're going to keep summing up a bunch of those, and then we're going to have the accumulation for the partial, or the last partial interval, in the last moment, or in the current interval, right? The amount of accumulation in the current interval. So nothing scary, right? This is exactly what we did above. So, but we got some question marks here. First question mark. How many things are we summing together? How many things are we summing together? No, but this could be in any, X could be anything. So what does that represent, what we're summing to? The number of completed intervals. The number of completed intervals. However many we completed, that's how many we're going to sum up. Okay? Now what are these X values that we're putting into R? What are the X values that we're going to put into R? So this is for now. So for a given completed interval, it's going to be R of what? R of what? So suppose here we are in the second interval. We took R of what in this second interval? R of 2. So it's going to be we're going to take the rate at the X value, the beginning X value of the J interval, whatever interval it is. So if J is 1, that's the first interval. We want R of the beginning X value in the first interval. That was 0.5. Now J is going to become 2. We're talking about the second completed interval. We want R of the beginning X value in that interval. And then we go on to R equals 3. Sorry, J equals 3, the third interval. We want the X value at the left side of the beginning X value of the J interval. And then finally, we're in the partial interval. What are we going to do there? Well, that's just going to be beginning value of the current interval. Beginning X value of the current interval. But you know what that is from the reading. What is the beginning X value of the current interval? That's what left X is. That's what left X is. It's only for the current interval. Left X does not apply to completed intervals. Okay? Left X is only one X value, and it's the left X of the current, it's the beginning X value of the current interval. It's not all of them. It's not all of the beginning values of all the intervals. It's only the current one. Okay? Now, this allows us to rewrite what dx is. How can we rewrite dx, right? So for instance, right now, x is 6 and left x is 5. What is dx right now? So how could we rewrite dx? If current value of x is 6, left x is 5, it's going to be the final value of x minus this initial value of x would give us dx, so it's going to be x minus left x would be dx. So, in order to get this function, then, we just need two things. We need the number of completed intervals for any value x, and then we need some way to figure out what the beginning x value is of the j interval. Okay, once we have those two things, we've got it. We've got that thing up there in one line instead of a line for every moment. Okay, questions on that? Yeah?
Sorry to go back on that, but you said that R5 dx, what's that considered again?
That's the accumulation in the current interval. That's the amount of accumulation in the current interval. Okay. Time to hit the books. It's hard stuff, but really important. I mean, so we're almost there. We've almost answered this question. You know how fast it's changing? You want to know how much there is.
because I want more time to study. It's just because it's fun to do it.
Cool, man. Glad you like it.
Have a nice day.
You too.
Thank you.